Okay, welcome. Let's look at 7.1. As you can see, the topic is area of a region between the curves, and we're going to be able to calculate out very precisely the area that resides between two curves. Just thinking about where we have been, maybe we had a quadratic equation in the past and we wanted to calculate the area between the regions 0 and 3. Well, what we've done up to this point is use the notion of Riemann sums to give us an estimate of the area. We've also used so rectangular spaces as well as trapezoidal shapes to estimate the area under the curve. But you know, there were always places where we had gaps. So, you know, these black spaces here, we weren't accounting for them. And we knew our method was a little bit imprecise. So today now we are going to learn how to run an integral that we can get the precise area. So from here I would say I was estimating the area between x being 0 and x being 3 of this quadratic function, and we would have an approximation of it if we used Riemann sums. So today we're going to come in with a whole lot more precision. And just to get this notion started, let's talk about where we're at here. I think it might be beneficial to label, whoops, that f is on there. Let's label this top function, at least it's top while it's in this region. Let's label that as f, and then this other function, let's label it g of x and f of x. Just for a reference, if you want to put that on all of these, go ahead, f of x and g of x. Now, let's just start with what we want to find. What we want to find, and I think you'll want to shade this, is I want to come in with the area between the curves in the region x equals a to x equals b. So I want to know in my case here what the lime green area is. And I notice here we had from a to b, so these would be x values. From x equals a to x equals b, they're going to be our vertical boundaries. In order to do this, what we're going to do is, let me get back to a crayon here, we're going to look at the area completely under f, which is our upper function along this space, and we will calculate its entire area. So shade that in. This would be represented by the integral of f of x dx running from a to b, and this would give me the orange area. Likewise, I could go compute the area that sits underneath g. And I'm going to use this red area here, the red crayon. And I could also calculate the area that resides underneath G. Well, what will happen if I take the entire orange area and subtract off the red area? Well, it will leave me this green area, won't it? So that is our approach. In order to get the area between f and g, we'll take the area under f and subtract the area that resides underneath the g curve. And we get this equation here that looks like the integral from a to b. These would be x values from x equals a to x equals b of f of x minus g of x. And you've seen the picture. This is our top function, and this was our bottom function on the region that we were interested in calculating the area. So it's top minus bottom. Now, would top minus bottom be a problem if I had one of my curves above and one of the curves maybe falling below the x-axis? Would that be a problem? Well, when we calculate this area, I would initially have my f function being this area, so maybe from this point B to, let's call this A. That would represent f of x in its area, so the integral of f of x from a to b. Over here, let's put this in pink. This would be the region between the curve and the x-axis for, let's call this my g function. So here's my g of x area integrating from a to b as well. Well, what happens when I integrate from a to b and I go f of x minus g of x dx, as shown in this calculation right here? Well, we know f of x would be positive. This is positive because it's above the x-axis. And this g of x would actually get a negative value. And look what happens to us. We end up with positive plus more area. So it will really add up and give us the total as well. So top function minus bottom function will always work. All right, let's go on and try a problem here so you can get a feel. Find the area of the region bounded by the graphs of y equals x squared plus 2. So we've got a quadratic lifted by 2, and y equals negative x, so linear function as shown, between the regions 0 and 1. And what I want to do then is let's just give ourselves a picture over here of what's going on. We're going to have left boundary being x equals 0, and the right boundary is going to be at 1. I'm just going to spot it here. X equals 1, so I'll draw a line down close. See if I can, let's just strike it there. So here's x equals 1. What we're interested in is this area that resides right in there. And I'm sorry, I should have extended this line so that it intersected as well with the linear function. So I want to find that yellow region. That's going to look like, okay, let's identify, let's call this f of x, and let's call this one g of x, and then go over and label it. So my quadratic is my f of x, my linear is my g of x. Set up our interval for the integration would be the area equals. The interval is going to run from 0 to 1. And now I want to do my top function minus my bottom function. I think if you keep this notion in mind, top minus bottom, it is going to serve you well. That is when we're running perpendicular. I want to calculate my area perpendicular to the x-axis. So that is going to look like, well, which is my top function? It is the f of x function for us, because that's the quadratic, minus the linear function g of x dx. And then let's substitute in the actual equation. So x squared plus 2 minus negative x for g of x multiplied by dx. Now, is that necessary to have d of x in here? Well, yes, it is, because it still takes off on this notion of a Riemann sum. Only thing is, here we're getting infinitesimally small delta x. We're going to let that rectangle get really, really thin, and we're going to have infinite number of rectangles between x equals 0 and x equals 1, which is what the integral process is all about. Remember, it really is defined as a limit. And so delta x getting small, we can say that it is dx. So I get, this is really width, and this is really the height of my rectangle. So height times width, we know, gives us area. Now, let's actually integrate, it looks like. So integrating, we'd have x cubed over 3 plus 2x plus x squared over 2 evaluated from 0 to 1. And we know how to do that. Plug in 1 first. 1 over 3 plus 2 times 1 plus 1 over 2. 1 squared is 1. Minus 0 going in. My first term would be 0. My second term is 0. My third term is 0. So I pick up an answer of, let's see, it'd be 2 plus 12 plus 3. I'm changing them all to sixths is what I was doing there. And that's going to give me 17 sixths. And that's the area under the curve. Try problem number 2. We want the region between the two intersecting graphs. Find the area of the region bounded by 2 minus x squared, and they called that f of x. Well, that's my quadratic, so that's this guy. And then the other one is just y equals x, so this is our g of x function. We want the area between the curves, so we're looking for, this region between here. And how am I going to set up my integral? It's a little trickier this time. I need to be able to take myself back up to the curve here and down to the curve here and figure out what x value this is and what x value that is, so that when I come to writing my integral, I know it runs between here and here. Well, the easiest way is to put in a calculator and ask the calculator to calculate the intersection points. But if I don't have a calculator and I have to do it by hand, which sometimes you do, we will just set f of x equal to g of x, and we'll solve the equation to figure out the intersection point. So I think since I see a quadratic coming, I'm going to move my terms over to the right-hand side so I get positive x squared. I already have the x there, and then subtract 2. If this factors, I'm going to be loving that, and it will factor, won't it? I'll get x plus 2 and an x minus 1, and I now found the zeros of my function where they intersect. Not really the zeros of the function, but where the two intersect. And that's going to be at x equals negative 2, and positive 1. And that, looks like I could believe it. It looks, about right, that I should have one negative x value and one positive x value. So now I've just been able to answer the question. I want to integrate from negative 2 to x being 1, and this is going to capture the area for us, so area is going to equal. Go back to that idea of top function minus bottom function. We'll get that length, and then that'll be the height of the rectangle, and then multiply it by the width dx. So now let's substitute in our top function really is f of x, is really f of x, and the bottom function is g of x, the linear function. Take that and put it into actual equations. 2 minus x squared, there's the f of x expression, and the g of x is x. And then we can integrate from negative 2 to 1. I think what I'm going to do is organize this. So I have negative x squared minus x plus 2 dx. And integration on this will give us negative x squared over 2 minus x. Oh, I messed up. Let me back up. X cubed, how about, over 3 minus x squared over 2 plus 2x. We want to evaluate this from negative 2 to 1, and now it becomes the fundamental theorem of calculus where we evaluate placing the top in first. So I'm going to have negative 1 raised to the third is still negative 1 cubed minus 1 squared is 1 over 2 plus 2. Subtract, throw in negative 2, that's going to be a negative of negative 8 over 3 minus negative 2 squared would be positive 4 over 2 plus 2 times negative 2 is negative 4. And if you simplify this out, you will find that you get 27/6, which reduces down to 9/2. And that is your answer. Okay, I think it's frozen up, so I'm going to stop right now, and then I'll pick up example 3, 4, and 5 in a minute. 15 minutes is a good time frame, so hang on.